Okay, the next talk is by Professor Tony Williams from Adelaide. Professor Williams, Professor Thomas.
Hello.
Professor Thomas. Oh yeah, he's there.
How are you doing?
Hi. Can you start now?
I hope so.
Yeah.
I'm trying to share my screen, but what happened? I can't see. Hang on. Let me just, I'm not sure what's going on. I see what's wrong. Okay.
Yes.
Okay, can you see that?
Yeah, we can see your screen.
Okay, let me just see if I can get full screen. Is that okay now?
Yeah.
Okay. So look, thank you very much for the opportunity to, I want to get rid of that too. Okay. Good. So thank you very much for the opportunity to talk on this occasion. It was a long time ago that I met Professor Mitra, but he made important impressions on me at the time. Just a few remarks on his work. How do I get rid of that? Just a couple of remarks I wanted to make about his work. It was remarkable how quickly he worked on both the Faddeev equations and the quark model within a year or two after the discovery of the Faddeev equations, and similarly after the suggestion of the existence of quarks. So I just noted a few of his publications that are worth mentioning. Already in 1965, he was talking about relativistic corrections to the Faddeev equations for the triton. He was also generalizing the three-body formalism to four bodies, something which, for practical application, took several decades beyond that. Quark model, he was working on it just a few years after Gell-Mann and Zweig. Calculating meson-baryon couplings in the quark model when many people didn't believe that quarks were real, but purely a mathematical artifice. In the 70s, joining together the ideas of low energy structure of the neutron and the deep inelastic structure functions. And touching on something earlier today with Stan Brodsky's talk, the light cone or null plane dynamics. These are remarkable papers and a great man. Let me come to the focus in my talk today. The relation to the work of Professor Mitra is through the Faddeev equations, which will be part of what I talk about. The main question I want to address is effective. Does anyone know how to get rid of this? Anyway, the question I want to address is effective field theory model independent? A great deal of modern nuclear theory uses effective field theory. The idea is that you construct a local nucleon-nucleon potential where the long distance chiral behavior is based on chiral field theory, chiral perturbation theory, and the short distance interaction is parametrized. But the point is that that interaction is local. The short distance parameters are adjusted to fit phase shifts over some range. And usually there's some power counting scheme to control the chiral theory. I remind you that power counting schemes are a human construct. They're not given by nature, and different practitioners are free to choose different power counting schemes. When you calculate the properties of a many-body system, either nuclear matter or finite nuclei, the two-body forces usually do not reproduce the data. And so one proceeds with the three-body problem in the same way. That is, the long-distance three-body forces are calculated using chiral effective field theory, and the short-distance three-body forces are adjusted in order to reproduce some selected set of data, either on finite nuclei or nuclear matter. And the claim is that this leads to model-independent predictions. I disagree with this. And the reason I disagree with it is I see no reason that the nucleon-nucleon interaction should be local. The nucleon is not point-like. It's a complicated eigenstate of QCD Hamiltonian. Its size is comparable to the distance between nucleons at saturation density. And there's no reason these complicated composite objects, which are not point-like, should interact through local forces. That is, phase shifts are not enough to constrain the theory. If changes in the two-body interaction, which don't change the phase shifts, lead to different predictions in nuclear matter and finite nuclei, then in order to reproduce those following the same prescription, you would need three-body forces, but those three-body forces would be different from the three-body forces you got with a local interaction. But the three-body forces, in terms of, say, Skirm theory or something else, are equivalent to a different density dependence in the interaction. And hence, the predictions for dense nuclear matter, or for finite nuclei for that matter, which involve different densities, will change. That is, they will not be model independent. So let me illustrate that with an old example, and I'm going back in time, but this is very relevant to what's being done today. So I'll give you an example from the three-body system. And this is work done with Irash Afnan a long time ago. The idea is to examine the effect of a unitary transformation which preserves phase shifts at all energies. We'll find that we constrain these unitary transformations by requiring that the one pion exchange tail of the nuclear force be unaffected and the charge symmetry not be violated. That is, that given A and N, which we can measure, that we should reproduce within reasonable error the scattering length for PP scattering. I'll illustrate this by showing you exact solutions for the three-body problem for the tritone binding energy and the ND scattering length. And for simplicity, the only part of the two-body potential which is transformed is the singlet S naught. For the three-body problem, it's the triplet S, triplet D, and singlet S naught interactions which are the most important. So how do we transform the Hamiltonian? We act on it with this is the strong nucleon-nucleon piece of the Hamiltonian. We act with a unitary operator to get a kinetic energy operator plus a different potential. The unitary operator is written this way, where HH is normalized to 1, and we take something that drives off exponentially and changes sign as 1 minus beta r. So there are two parameters in the unitary transformation. If the potential appearing in the Hamiltonian here is local, the transformed potential will have a velocity dependence, and hence it's non-local. Now, if we look at transformations, beta's been fixed to 1 Fermi. Let me go back. Beta's been fixed to 1 inverse Fermi, and we vary alpha. You see the change in the short distance wave function, chi of k, as a function of that parameter in the exponential alpha. If alpha is very large, there's very little change from the unperturbed value. And as alpha gets smaller, the changes get bigger. Now, first of all, we don't want to change the long-range tail. So we remove these two, alpha equals 2 and alpha equals 2.4, because they modify the potential beyond 3 Fermis by an amount that's too great. So if we look at the effect on the triton binding energy and the doublet scattering length for ND scattering, we see here the Phillips line. This is the original Hamiltonian. And this is the result as we decrease alpha. And so if increase to larger distances, the change in the transformed Hamiltonian, in interacting Hamiltonian. And we see as we do it, we move along the Phillips line. Alpha gets smaller, we move back along the Phillips line. And when we get to alpha 2.6, we start to deviate from the Phillips line. This is the region where we've changed the one-pion exchange nature of the nucleon-nucleon potential. And so we exclude that region. Also, if we stick with alpha to be bigger than 2.8 or bigger, we preserve charge symmetry. That is, ANN and APP are consistent within 1%, which seems reasonable. However, all of the points along the line between 2.8 and alpha equals infinity are allowed. They all give exactly the same phase shifts to 0 to infinity. The only thing you're changing is the degree of non-locality in the two-body interaction. If, for example, you chose to reproduce the experimental value of the triton binding energy and the measured doublet scattering length by introducing a three-body force, the three-body force you would introduce with this interaction, with this interaction, with this one, with this one, with this one, those three-body forces would all be different. And so your predictions for nuclear matter or finite nuclei would be different. That is, they're not model independent. Now, what's this got to do with nuclear matter? Well, Fritz Coster and collaborators, including Ben Day at Argonne Lab a long time ago, carried out a similar study of the saturation curve for nuclear matter, in symmetric nuclear matter. And you see here the binding energy versus density. The correct saturation point's about here. But you see, as you make unitary transformations on the Hamiltonian, you can change that saturation point by an enormous amount. In every case, if you introduced a three-body force, in order to reproduce the experimental value of the binding energy and saturation density, your three-body force would vary enormously. And hence your predictions for the properties, for example, of neutron stars would vary dramatically. That is, your predictions would not be model independent. Okay, so why am I concerned about this? Because I'm interested in a fundamental description of the atomic nucleus. And so let me just go through a few things which are of particular interest in this context. There are two views of nuclear structure. The EIC is concerned with mapping the quark and gluon structure of atomic nuclei. And implicit in that is that it's different from the quark and gluon structure of a free nucleon. On the other hand, nuclear physicists, many, believe that considering quarks is in contradiction to our modern understanding of nuclear physics, because the energies relevant for nuclear physics are only a few MeV. I believe that this second statement is wrong, and it's wrong for the following reason. We know that the intermediate range nucleon-nucleon force is a strong red scalar. In relativistic treatments, it's typically between 300 and 500 MeV. That's half the mass of the nucleon. It's not small. And so the argument that the mass scale in nuclear physics is different from the mass scale associated with quarks is quite wrong. It's true that the scalar attraction is cancelled by a large vector mean field, but that's a Lorentz vector. And its effect on a nucleon in nuclear matter is really just to shift its energy, whereas the large scalar field can change its internal structure. That's led us, starting with work by Pierre Guichon many years ago, it's led to the development of the quark meson coupling model, where we start with a quark model for nucleons, and originally the MIT bag, later the NJL model. You introduce relativistic Lagrangian density with coupling of sigma omega and rho mesons to the non-strange quarks, and also the pion, but I'm emphasizing here those that develop a mean field in nuclear matter. Initially, just 4 parameters: the coupling of these mesons to the quark, and the mass of the scalar field, which is not known. Fit those to nuclear matter properties and apply them to finite nuclei. Now, recently, we found we needed a 5th parameter in order to describe the giant monopole resonances. But implicit in this model is that the coupling of the sigma field to the quarks, to the confined quarks, means that you have to solve consistently for their internal structure. So we start with quarks. We go to nuclear matter. From that, we can go to neutron stars or dense matter. We can also get density-dependent effective forces and calculate the properties of finite nuclei. In nuclear matter, the effect of the change of the internal structure of the nucleon is that instead of the mass decreasing linearly with the mean scalar field, there is a tendency for the internal structure of the nucleon to rearrange in order to oppose that. And that's characterized by what we call the scalar polarizability, by analogy with the electric polarizability, if you applied an electric field to the nucleon. In the bag model, it's about 0.2 times the bag radius. This is equivalent to having repulsive 3-body forces. For nucleons, 3 nucleons, a hyperon and 2 nucleons, 2 hyperons and a nucleon, all predicted by the model with no new parameter. It's entirely determined by this scalar polarizability. Now, one interesting thing when it comes to neutron stars is that the sigma field enhances the spin-dependent gluon exchange interaction between quarks, increases the sigma lambda mass splitting in medium, and hence we find no sigma hyperons in neutron stars at 0 temperature. I want to show you just a few results from finite nuclei. So this is across the periodic table, some 820 even nuclei. The color coding is the light green means that we're very close to the experimental binding energy. And you see that's true above the lighter nuclei, above N about 40 and Z about 20. The RMS radii typically agree within 0.1%. If we compare this, the most recent version of this model, QMC Pi 3, the RMS deviation across those 820 even nuclei is 0.29%, which exceeds the accuracy of all other models except FRDM, which can't predict the charge radii, and has more than 25 parameters. This approach has just 5 parameters. If we look at super heavy nuclei, QMC pi 3 are the red points, and the average deviation for super heavy nuclei, that is Z greater than 100, is 0.03%, which is outstanding compared with any other theory of super heavy nuclei. The super heavy nuclei were not fit. It was 70 nuclei across the periodic table, but much lower mass that we used to choose those 5 parameters. You can also calculate hypernuclei with no new parameters. You simply calculate the interaction of these fields with the non-strange quarks. It's the agreement with the 1s state in lead for lambda in lead is probably too good. More reasonable would be the 2 MeV agreement or 3 MeV with the others. This is a bit too good. But nevertheless, it gives a very realistic description of lambda hypernuclei, and it's also consistent with the few measurements of cascade hypernuclei. Let me come to neutron stars. Here we see the so-called model-independent equation of state developed by Anala et al., the green region being the preferred region. In this region, they used effective field theory, but effective field theory doesn't apply to neutron stars at low density because the surface of a neutron star is extremely complicated. It involves exotic nuclei, not neutrons and protons, exotic nuclei and pasta-like structures. And this model uses, in this model, we use a proper equation of state for the low density region in neutron star matter. But once we get above that low density region, and we're talking about neutrons, protons, and hyperons, we agree with the preferred region of Anala et al. And in particular, the kink here is associated with the production of hyperons in the core of the neutron star. Now, recently, neutron stars have become a hot topic because of new data coming from gravity wave experiments, LIGO and Virgo, and also from NICA, the satellite measurement of hotspots on neutron stars, from which you can hope to deduce the radii and masses of the stars with reasonable errors. I show you the plot of mass in units of solar mass against radius for a neutron star with the constraints from LIGO and Virgo and from NICA, with and without hyperons. And you see that at least at the moment, this same theory, but now relativistic, whereas the finite nucleus calculation was of necessity a non-relativistic reduction. But for neutron stars, you have to have a relativistic theory. And you see that for the moment, this theory is also consistent with the neutron star data and the tidal deformability coming from the quadrupole deformation of the neutron stars as they are about to merge with each other. One fascinating thing for someone not working in this field is that the core of a heavy neutron star, and in this case, this is the structure of, as a function of radius, it's the baryon content of the neutron star. So this is the fraction. And so this is 20% cascade minus, and that extends out to 5 kilometers. So for a heavy neutron star, this theory predicts that it consists of a huge amount of strange matter out to 5 kilometers, which is a pretty remarkable object. In summary, since my time is pretty much up, the complicated structure of the nucleon and hyperons suggests to me that the assumption of locality for two-body forces upon which effective field theory is built is too restrictive. If you allow non-locality, and in particular, you look at phase shift equivalent interactions, which don't perturb the long-range behavior of the interaction, you find large changes into predictions for three-body systems and nuclear matter. As a consequence, the three-body forces, which in effective field theory are used to patch up disagreement with experiment, are not model independent. And as a consequence, the predictions for dense matter are not model independent. And I believe that there should be a lot of interest in approaches such as the one I described, quark meson coupling model, which are not built on chiral effective field theory, but actually describe data extremely well with many less parameters. Okay, I just wanted to to acknowledge a number of the people involved in the work I've described. Thank you.
Thank you, Professor Thomas, for a very comprehensive discussion. Now, any questions on this lecture? Questions, comments? Probably not.
Ah, well, that's a shame. Okay, I'll stop sharing. Thank you.
Yeah, let's thank both the speakers.